A second type of electric thermometer we want to look at is called a thermistor. Now, thermistors are thermally sensitive resistors formed from complex metal oxides. Here's an illustration. So a metal oxide powder is compressed into a pellet, and its resistance will change with temperature. So by connecting it to an ohm meter, a change in resistance would indicate a change in temperature. Now, they might remind you of an RTD, but there is a significant difference. Recall that with RTDs, as the temperature increased, the resistance increased in a linear fashion. With thermistors, it's quite the opposite. As the temperature increases, the resistance decreases in a nonlinear fashion. And recall that an RTD is made of a conducting metal, whereas a thermistor is made of a non-conducting resistor, so they would be expected to behave differently. Furthermore, the temperature coefficient, that is the slope of this R versus T line, if you recall, was pretty small. The example we looked at was 0.004 per Celsius degree. That's not a big response. It required a fairly large temperature change to get a small change in temperature. On the other hand, the temperature coefficient for thermistors is designated by the term beta. Beta is typically quite a bit larger than alpha, and so we'll see that a fairly large resistance change occurs for a relatively small temperature change, and so they're quite a bit more sensitive in that regard. We'll look at the formulas in just a minute, but let's read a little bit further here. Thermistors produce relatively large changes in resistance with temperature, so that high precision temperature measurements are possible. When thermistors are connected into bridge circuits like the Wheatstone bridge, and we'll talk about this a little bit later, very small temperature changes such as 0005 Celsius degrees can be detected. Furthermore, long leads can be used, since the resistance of a wire lead, a metal conducting wire lead, would be negligible compared to the resistance of the thermistor. What are we saying here? We could use long leads to the actual meter from the sensor, made of copper wire, because copper has very low resistance and it won't affect the readings of the thermistor sensor. Why would that be important? Why might you want long leads? Well, perhaps you have your sensor, your thermistor, in a location that you wouldn't want to be in. Perhaps it's unsafe, maybe it's hot, dangerous. You could have your meter where you read it quite a distance away, and you can read it accurately and safely. Let's take a look at the formulas that describe the temperature resistance relationship in thermistors. You'll see that the basic equation here is resistance at some temperature equals R sub 0, that's at the freezing point, times E raised to the beta, which is the temperature coefficient, times 1 over T sub 0, that's the freezing point, minus 1 over T. Now, one important difference between the formulas for RTDs versus the formulas for thermistors, and you need to remember this, is that for thermistors, the temperatures are always recorded in Kelvin, not Celsius. Now, I've broken this formula up over here so we can get a better look at it. So clearly this is not a linear equation, it's exponential, but we can linearize this. Let's take the ln of both sides of this equation. We'll plot, say, the ln of R. And we'll take the ln of this side, R sub 0, times E to the beta 1 over T sub 0 minus 1 over T. Now, the ln of a product is equal to the sum of the lns. So I can write this as I have below here. The ln of this term on the right can be written as ln of R sub 0 plus the ln of E to the x. Now, the ln of E to the x is simply x, so this term simply becomes, well, it becomes our term here. Right? So this clearly then is the equation of a straight line. Y is equal to m, our temperature coefficient, times x plus b. So we could plot this and expect a linear relationship. If we plot the ln of R, versus 1 over T sub 0 minus 1 over T in Kelvin, we can expect to get a relationship. It'll be a straight line, but it will have a negative slope and look something like this. And this point right here will be the point 0 ln r sub 0. Let's go a little further with this. We could transpose ln r sub 0 and write ln of r minus ln of r sub 0 is equal to beta times 1 over T sub 0 minus 1 over T. We know the difference between two logarithms is the logarithm of the quotient. So ln r over ln r sub 0 is equal to beta times 1 over T sub 0 minus 1 over T. And again we have the equation of a straight line. Y is equal to m times x. So looking at this equation, if we were to plot the ln of r over r sub 0 versus 1 over T sub 0 minus 1 over T, again we get a straight line, but this time b is 0, so that means it's going to travel right through the origin. It's going to look something like that. And this point, of course, is the origin 0, 0. So we can handle that quite easily. On our calculators, we can do regression with it. Easy to handle. There's one application here I want to mention before we leave this. Thermistors can actually be used as flow indicators as well as temperature sensors and temperature controllers. Now the last unit in this course deals with flow measurement, but it presents itself here, so let's talk about it for a minute. So you could picture, here I have a thermistor that is immersed in a pipe, and the fluid is flowing through the pipe. Now we're applying a DC current, so we're in this direction, we're forcing DC current through our semiconductor, so not much current will flow. So owing to the applied voltage, it will heat up a little bit. At the same time, picture that a fluid is flowing through the pipe, and this fluid could be a liquid or a gas. If the fluid is colder, it will cool down the thermistor. At some point, as long as the fluid flow is constant and the current flow is constant, then this thermistor will reach a constant temperature, and hence the resistance on the meter measured here will be constant. What happens if the fluid flow were to speed up? So let's just add another arrow here. If the fluid flow were to increase, that would cool down the thermistor. So if we use the symbol Q for flow, if the flow rate were to increase, then the temperature of the sensor would decrease. Now when the temperature of the sensor decreases, if you look at the graph, the resistance will actually increase. So actually, if you see an increasing resistance, it would indicate an increased flow rate. What happens if we actually decrease the flow rate? Let's take away one of these arrows. So if the flow rate was going to decrease, that would mean there'd be less cooling, so the temperature of the thermistor would increase. The temperature of the thermistor increases, what happens to the resistance? The resistance will decrease. So a decreasing resistance on the indicator would indicate a decreasing flow rate. So in fact, the thermistor can be used as a flow indicator. We'll look at flow rate in greater detail at the end of this course, but here's a great application for it. There are two problems related to thermistors, problems 7 and 8, on page 29. So let's take a look at those next. So on page 29 we have questions 7 and 8 dealing with thermistors, and let's start with question number 7. It says a thermistor with a temperature coefficient beta of negative 4012 has a resistance of 7,759 ohms at the freezing point at 0 degrees C. Calculate the resistance at 120 degrees C. So our formulas are in terms of resistance, so it should be simply a matter of plugging these values into our formula to calculate R. Now this resistance of 7759 ohms is at 0 degrees C, so that would be R sub 0. We're calculating the resistance at 120 degrees C. One of the things you must keep in mind is that for the thermistor calculations, they are in Kelvin degrees, not Celsius. So we must convert. Now, it seems tedious for me to write this all out for you, so I've gone ahead and written it out. I'll just kind of walk you through it or talk you through it here right now. We've got two different formulas we can use. Let's start with a direct calculation of resistance using the exponential form of the equation. R is equal to R sub 0 times E to the beta times 1 over T sub 0 minus 1 over T. So we're given that R sub 0, that's at the freezing point, is 7759 ohms, times E to the beta, which is negative 4012, times 1 over T sub 0, working in Kelvin. T sub 0 is the freezing point, that's 273.2 Kelvin, minus 1 over the temperature we're trying to calculate at. That was 120 degrees Celsius. We add 273.2 to that, get 393.2 Kelvin. So 1 over 393.2. Now I'm carrying the extra decimal here because this is in the exponent, and a small difference in the exponent can make a significant difference in the value, so I'll carry the extra digit here. So the numerator here evaluates to, 1 over 273.2 is 00366. 1 over 393.2 is 0.002543, and the difference is 001117 multiplied by negative 4012 gives us negative 4.4818, and E to that number is 0.1131. Multiplying that by 7759 ohms gives us 87.8 ohms, and that was at 120 degrees Celsius or 393 Kelvin. So let's just think about it for a second. Make sure this makes sense. At 0 degrees C or 273 Kelvin, and just rounding things out to think about them, we had a resistance of 7759 ohms. At an elevated temperature of 120 degrees Celsius or 393 Kelvin, look at how much the resistance dropped. It dropped to 88 ohms approximately. Does that make sense? Well, because this relationship is not direct, it's inverse and it's exponential, it's quite possible. So notice that as the temperature is increasing, the resistance will be decreasing. That's exactly what we've seen, and it's quite a dramatic drop because it's exponential. So at least it makes sense conceptually. Now, one of the things that I've asked you earlier in this unit is to determine or tell me what the units of beta are. So recall in RTDs, our temperature coefficient, you were given units of Celsius degrees to the minus 1. What would it be here? Let's go back and look at the equation. So here we're calculating resistance in ohms, and this number, this value, is 7759 ohms. So the unit of ohms has to be what we want, and that means that everything that follows has to become dimensionless. Whatever units we have in here have to cancel. So this is beta. What are the units of beta? Well, up here in the exponent we have 1 over T sub 0 minus 1 over T. This will be 1 over T. So this 1 over T must be cancelled by the units of 4012, whatever they are. So you see this has to be Kelvin. So Kelvin times 1 over Kelvin would cancel. And that, therefore, 7759 ohms gives us units of ohms for the answer. So the units of beta must be Kelvin. Kind of odd, but it must be the case. Let's look at this using the logarithmic form of the expression. Ln of R equals the ln of R sub 0 plus beta times this term 1 over T sub 0 minus 1 over T. So the ln of R sub 0 is the ln of 7759. Beta is negative 4012. We've already worked out this term, so I won't walk through it again. I'll just give you the value. It's 0.001117. The ln of 7759 is 8.957 minus this term becomes 4.4814. The difference is 4.4756, the anti-ln of which is 87.8 ohms. So they both work just fine. Question number 8. We're asked to calculate the temperature coefficient beta, R sub 0, the resistance at the freezing point, and the temperature in degrees C at 15.1 ohms for thermistor data that's given in a table. So we're given two data points, 4 degrees C, 59.8 ohms, and 74 degrees C is 5.5 ohms. So what is the temperature that would generate 15.1 ohms? Also, what is the temperature coefficient? What's R sub 0? This is not as easy as it might seem, not as direct. Beta is the slope of this line, the plot of ln of R versus 1 over t sub 0 minus 1 over t. So we could not get that directly by putting any of this data in the calculator. As shown, we'd have to rearrange it a bit. And ln R sub 0 would be the intercept. So if we were to plot ln of R rather than R, and 1 over t sub 0 minus 1 over t, both in Kelvin versus instead of degrees Celsius, we could then use that plot and obtain the intercept and the slope, and we could forecast from it using linear regression. That's what I'm going to do here. And now it's pretty tedious for me to write it all out, so I've gone ahead and done that, and I want you to just follow with me. So I'm going to use first this linear equation. Ln of R is the ln of R sub 0 plus beta times 1 over t sub 0 minus 1 over t, in which the slope of the line that we obtained from the calculator will be beta, the temperature coefficient, and we'll get the ln of R as the intercept, and we'll get then the anti-ln. I put this in a table, as you see here. Here's the data we're given, t and R. But I want to get the ln of R, so I took the ln of these two values, and I want the ln of 15.1 ohms, which is 2.715. Now I need this term here to plot, 1 over t sub 0 minus 1 over t. That'll be 1 over 273.2 minus 1 over 277.2, which is the 4 degrees Celsius, but now in Kelvin. This is 1 over t sub 0 minus 1 over t for a temperature of 347.2. Once you enter the first two data points in the linear regression mode of your calculator, you can then recall the values for A and B. This is the form of the linear equation, y equals a plus bx, that the calculator fits the data to. And b is the slope, minus 3281, temperature coefficient. And a, when you recall A, that'll be the ln of R, which is given as 4.262. You'll want the anti-ln, which is 71.1 ohms. Now you can then enter a value of 2.715 and go second function recall x prime to get an x value of 0.04722, from which you have to calculate the temperature in degrees Celsius. So let's write it out here. X prime is 0.04722. That's equal to 1 over t sub 0 minus 1 over t. Now 1 over t sub 0, 1 over 273.2 is 0.00366. And now it's just a matter of carefully rearranging terms. I'm bringing 0.04722 to the right. I'm bringing the negative 1 over t to the left to make it positive. I'll have 1 over t is equal to 0.00366 minus 0.04722, which is 0.03318. So T will be the inverse of that, which turns out to be 313.7 Kelvin. I want the Celsius temperature, subtract 273.2, and it's 40.5 degrees Celsius. Oh, tedious. Make sure that you actually do this. I appreciate that you can follow me doing it, but I've had students on several occasions tell me that, sir, I see what you're doing, but I can't get it on my calculator. So take the time to plug these numbers in your calculator and make sure you can do the regression handling on the calculator. It's really important. You'll need it for the tests. Now you can also do this using the other equation, the exponential form. R is equal to R sub 0 times e to the beta times 1 over t sub 0 minus 1 over t. In this case, you can plot R values directly as y, and x values again would be 1 over t sub 0 minus 1 over t. Be sure to enter this data into the exponential regression mode of your calculator, STAT3. This is not linear regression. So you'd enter these 4 points into the regression mode of your calculator, x and y, x and y. You can then recall the regression coefficients. This exponential equation will have the general form y is equal to a times e to the bx. So when you recall a, it'll tell you that it's 71.12, which is in fact the resistance. Look up here, R sub 0, 71.12. And the recall b value, 3281 with a negative sign, that's the temperature coefficient beta. So you get those directly from the regression coefficients. And then you'll have to then forecast the x prime value for a resistance of 15.1 ohms and it's 004723. And you can evaluate what T is just as we did over here. Again, it's the same value, 40.5 degrees Celsius. So not too difficult to understand, but definitely is tedious, so take some time to work through that problem. You might see something like it on a test. So that'll be it for our study of thermistors.